Hello everyone, and welcome to the Milestone 4 presentation for FogFarms, the farm management system for commercial growing. Before we get started, I would like to provide an outline of our presentation to help you, the audience, follow along with our presentation better. We're going to start off with the introduction to our system, what FogFarms is all about. Then we're going to discuss about database. After that, we're going to discuss about the SQA, the software quality assurance testing we performed on our system. Then the data analytics, and we're going to end our presentation with a live demonstration of our system. So let's get started with the introduction to our system and our team, FogFarms. Our team, FogFarms, has set out to create a farm management system for the future farms that will utilize fogponics as the method of growing plants and at the same time increasing the efficiency of the traditional farming methods. In order to achieve that, a variety of development tools were used. To develop the system, Visual Studio Code and Golang are the integrated development environments of choice, or IDEs. The Node MCU was programmed using the Arduino IDE. Docker was used to create a Postgres SQL containers for development and testing. Our server is deployed on Heroku, with the reason being that it's free. And GitHub Action is our continuous integration and continuous deployment tool, which automatically builds and deploys the system to Heroku. Next is the hardware, the sensors and devices used in order to control and monitor the growing conditions of the plants in the farm. It consists of an ultrasonic fogger, which is used to turn the nutrient solution into fog, a DHT11 sensor used to measure the humidity and temperature of the air, a TDS sensor used to measure the total dissolved solid in the nutrient solution, the lux sensor used to indicate the amount of light density the plant is receiving, the water level sensor used to help control the amount of water or the nutrient solution within the grow box, and the solenoid valve, which used to control the amount of nutrient solution inputted into the farm from the nutrient unit. Next is the system architecture, which flows as the following. The Node MCU reads data from the sensors along with the status of the devices and sends them to the server via a HTTP request, which then stores the data as a record in the database. Under certain conditions, the server will respond with the device status from the database to update the Node MCU. To refresh the sensor data and device status, the front-end client sends a HTTP request to the server. The server then queries the data for the latest entry and sends it back as.
For our database, let's start with the ER diagram. There have been many changes to our system's database structure during the course of development. Initially, we tried to normalize as many of the tables as possible. However, given the way the system works with the front-end and IoT elements, some tables had to remain unnormalized. For example, the sensor data table is one of our unnormalized tables. The multi-valued attributes are the ones storing the sensor data. This is because a single module can have multiple nutrient units and grow units, making the length of each record vary from module to module. Limitations of the system. The system was designed to work with computer screens. Therefore, usage on mobile devices is not recommended. The current version of our system uses the Heroku Postgre free HobbyDev plan. Therefore, its limitations are 1 user per database, 20 maximum connections, and 10,000 maximum row entries from all tables. Indexing. The indexing in our database consists mainly of the indexes generated when defining primary keys and unique constraints. To improve performance, we've created 2 other B-tree indexes on the attribute permission level of permission table and timestamp of sensor data table, since they are the most often used search conditions. Constraint enforcement and handling. In our database, the primary keys of all tables are auto-incremented integers, ensuring that they won't have null values and are unique. Currently, our system does not support the change of primary key values, since updating a single key could mean updating all the other entries from the tables that reference the single key being updated. Null values are also prevented. Instead of null, we use 0 values. That means, for varchar, it's an empty string. For integers, and floats, it's a 0. For Boolean, it's a false, and for arrays, it's an empty array. Integrity constraints. In our database, all integrity constraints are defined when creating the tables. Note that the action taken on delete is set default for all foreign keys in every table. This is because each entity table has a zero-value entity with each attribute containing the zero value for its data type.
To the software quality assurance or SQA, in which we do to make sure that the software meets the requirements given, ensuring our customer satisfaction and for an effective application. Majority of our reviews have been informal real-line chat or video call. A routine for an informal meeting is on every Friday afternoon. Another informal review is to review to report. Our reviews have been done throughout all phases of SDLC, in which requirement, functional models, structural models, and design models are consistent and conform to the original needs of the users. The benefits of informal review is that we get quick feedback and correction as there's no setting up for formal meeting. Also, there's more flexibility of times. Error can be reported when reviewer are freeze and corrected when the producer are freeze. Pair programming is also implemented. Let's take a look at coding pair programming in our group. We have Gil who writes code and pushes them to GitHub, and Dave who creates a branch, debug, commit, and makes pull requests. Both of them can discuss if there's any conflicts before merging the branches. If there's any errors, Dave will report the errors and may correct the error himself. Gil may also report the error to Dave for assistance. This kind of implementation, you can see that Gil focuses on the functionality of the code, and Dave does the quality assurance and does some collection. System requirements, design document, and the implementation are reviewed with a formal technical review approach. For the requirement checklist, we separate it to see if it's necessary, if it conforms to user's need, and if the conflicts between requirements have been resolved. For the design checklist, we check to see if it conforms to the identified requirement. We check for cohesion and coupling, and if it conforms to the principle of UI design. For the implementation checklist, we ensure if the ability of software products fulfill the requirements. For the functional requirement of the user management, we use that the system shall allow the administrators to give supervisors authorization level to selected users. It's necessary as there may be one more user who works on the farm, so different levels of permission for the users must be applied. It conforms to the user's need because the admin must be able to add or remove users, and the users have to be able to change their password. The conflicts between requirements have also been resolved, as there's no overlap with other requirements and we have consistency with other requirements as well. Another example of the non-functional requirement on the performance is necessary as it provides real-time monitoring, and we check that it provides a means for the owner to constantly measure the value of the system, as based from the interviews, the user has to be able to measure those values such as the pH and TDS, or else it could be fatal to the pants. For the design checklist, design models are checked for consistency and conformance to the requirements. Example, the deployment diagrams, we give it a path for the consistent with the network model. It has to provide connectivity to deliver operational requirements and functional requirements. And for the web page design, we have to make sure that it conforms to the standard design principles, and it's a pass if every list in the principle of UI design is present. To make sure that the code and system actually works, we separate the testing into unit testing, where we use the white box testing approach to test the logical structures of the component to ensure that there's no errors. And then we perform the integration testing using black box testing to test the interface between two or more components, making sure that they can combine to become a larger component. For the testing in hardware, we do unit testing first and then we do the top-down approach integration testing. For front end, we use Big Bang, where we test everything at one time due to time constraint. Next, for back end, after testing separate function, we do the bottom-up integration testing. System testing is done to combine other parts, the back end, the front end, and the device to see if they can work together cooperatively.
Okay, with all the data that we are collecting in our database, we definitely can use them for data analytics in order to gain insights or see some patterns within the data. Our current plan is to do data analysis on historical data using Python in Google Colab. We will also convert tables stored in the PostgreSQL database to a CSV file, which will be imported into Google Colab. There are several questions we can ask of our system to gain some insights from, one example of which is how well the equipment in our system actually works. Well, how do we measure how well the equipment in our system actually works? Let's compose a more specific question than that. Let's say, over the course of a month, how many times does the type of sensor data, for example TDS, deviate from the parameter set by the user? By, for example, 10%. What we need to do is compare the sensor data within a module with the parameters set for the module group during automatic mode. But for simplicity, let's focus on one sensor value, TDS, short for total dissolved solids, which measures how much nutrients are dissolved in the liquid. You might be wondering what the benefits for analyzing data from this question are. First, we can look for patterns of abnormalities. Second, we may be able to detect device inefficiency or aging, etc. And third, we might just understand the data better. In this example, I have made some assumptions. We will use only the TDS sensor data, and when the user sets the TDS parameter to 600, they do not change it in the analysis period. And the sensor data is measured during automatic mode, so that the data should only deviate from parameters set due to other factors than the user change it. To collect data in PostgreSQL, first we join tables in PostgreSQL and store the result as a table. We will get the TDS sensor data for a particular module group and module. Here it is module 1 from module group 1. We then export the table to a CSV file. The module group action table logs whenever the mode of the system is changed between automatic and manual. We extract the module group action table for only module group 1. We then export the module group action table to another CSV file. Now, we have a table with TDS sensor data for module 1 and the ranges of time the module group 1 is on automatic mode. For this example, we use generated TDS data for 1 month, measured at every 2 seconds. We use data generated randomly in Excel. These are the Excel functions used for each table, the TDS data and the module group action data. With all the data ready in Google Colab, we first import the necessary libraries for data analysis. Then we upload the CSV files, which will be stored on the Colab temporary storage. Then we convert the CSV files into the data frames to be analyzed. We create a data frame which only stores the sensor data for time range during on-auto mode. This is the time range when on-auto mode changes from true to false. And if the last on-auto mode entry is also true, we also include its time range.
We can use the following command to plot the data.
As you can see, the TDS sensor data during the on-auto mode has a normal distribution, and changes seem random with no specific trend. Of course, in real sensors, values may not be this way. We then create another data frame to store only the filtered data sensor that is beyond the 10% range of 600, which is the parameter set. Alright, to answer the initial question, over the course of a month, how many times does a type of sensor data deviate from the parameter set by, for example, 10%? We can count the number of data records beyond 10% of the TDS parameter in this month. It is 322,522, nice number, which is 24.89% of the TDS values. If we want to take a closer look at the data, we can ask at what time of the day is there an abnormality, a deviation of 10% for example. Since we're already working with a data frame containing only deviations, we can get the timestamp stored when the deviations occur for one particular day and convert it to date time. And here, we can see that we have sensor deviations every hour. This means there could be problems with the TDS sensor or the mixer.
Next, let's take a look at the demo version of FogFarms